reception. This is a pretty long talk, but since you are famished, you are hungry, and Sir also wants to leave quickly, he has some other function elsewhere. What I'll do is, I'll try to focus on the critical aspects. Now, I am going to present with the intention of exciting only the younger people here, alright? So I request you people to play along. Yeah. This part, we'll just try to show you certain things that you might have seen in your textbooks while you studied, but you did not ask certain fundamental questions. Okay, now this is sun. You see it here. So there are different types of cells, and this part is the rods and cones. And then you have, if this is the retina, you have blood circulation here, blood here, and then the nerves, they arise from the rods and cones here, and they come all the way and go into the optic nerve. Alright? So, in the classical theory, rods and cones are deemed as the fundamental units of vision. Now, basic chemistry is that, this is the retinal cycle, it's neuronal. So, now, photon falls, this is the active, photoactive chemical in the protein called rhodopsin. Rhodopsin. Photon makes cis to trans. Alright? And then this cis to trans movement or the photo-induced change gets a lot of things going. I'm not going to go into the details because that's beyond. So, and then it pops out and that sends a signal to the protein that's adjoining rhodopsin on the membrane, and then that leads to, that's called, GPCR, transducin, it's a protein, GDP binding protein. So it leads to activation and conformation change. One thing that biologists are very excited always about, and they don't understand, they always invoke conformation change. Yeah, well, I don't say that it doesn't exist. Definitely it does. But then not every signal transduction, not every receptor ligand interaction leads to a conformation change. Certain things you cannot explain otherwise also. Then there is phosphodiesterase, which leads to a cyclic GMP cascade. Now this is how a rod cell would look like when looked closely in conjunction with the retinal pigment epithelium. So it has mitochondria, it has got the synapse, then there are this disc. This is called the outer segment. Alright? So let's, and then the resting and excited states are characterized where there are different types of bind. The resting state is like this, and the activated state is photon trans. It becomes that GDP, GTP is bound, and then the calcium ion channels and cyclic GMP cascades and all are activated. I will try to just give you a brief view of what it looks like in the classical perspective. Photon hits, it jumps out, it somehow triggers a GPCR activation, transducing, somehow the alpha transducing breaks free, goes, first what happens is the GDP that is bound, it gives way to GTP. GTP is preferred, and then the alpha transducin breaks free and goes and binds to phosphodiesterase, and there is a signal cascade. So the rationale of exchange of GDP with GTP is the key signal transduction by GPCR or transducing. Alright? So now this is the part that I want all of you to focus. How do you do something new? You do something new when you question something that is old. Alright? That's where your relevance comes. If you have seen a wonderful movie called Robots, it's a Pixar movie. There's a character called Oscar Wilde. He says, find a gap, fill the gap. That's where you come in. Whether a scientist or an engineer. Scientist explains a natural phenomena, engineer solves a problem that mankind faces. So you need to find a gap and fill the gap. So now I look at the problem like this. When I was your age, I had seen it multiple times, but then here is the problem. This is the structure of the eye. You see multiple layers, approximately you see. Now you see this so many layers of different components, many of which are active. Blood flows in, activity, cells, components have provided movements, all that. So I'm not going to go into the details of the anatomy. The point is this, that the signal should rise somewhere here. It should travel all the way and then go like this. This is the action potential. Now, I do not understand why, if this were the case, why didn't we have a simple system where the rhodopsin was, the rod cells were facing this way, and you had a simpler system. You just need a diffuser. The classical theory says that our eyesight evolved to take care of diffuse light. If that is the case, just a diffuser. It need not go through this. The problem is, roughly you say 350 to 400 nanometers, microns is the thickness of the retina. Now, a photon of 400 nanometer wavelength, the shortest one. If it has to traverse 400 micron, it has to traverse how much times the wavelength? 1,000 times. So suppose a photon arises here, comes here, goes here. Now here, it will go through, before traversing this, it will go through reflection, diffraction, all the different kinds of processes. What is there to prevent it from happening? So, if you get some signal like that, and it falls on retina, a photon comes from here, once it will come here, it will go here with a different cue, and sometimes it might come here with a different cue. How could you possibly ever evolve a photoreception system with this kind of a setup, where rods and cones are the primary phototransducers? So that is the fundamental question that I ask. Then the structures of the protein is all. Now this is the rhodopsin, this is the transducing complex. Now rhodopsin is not, see how can we know there is a omega? There is no role whatsoever for this cyclic kind of a protein there. Alright, this is alpha transducer. The point is, both GDP and GTP bound alpha transducing structures are known. There is no real conformation change. It's practically one line over the other. Hardly any difference. So how does the classical rationale get explained? So now there is no role in the classical theory for oxygen in vision. Where we find retina, both sides are highly innervated by blood cell, blood vessels. So why do we have blackouts in hypoxia, proximal and distal surface vascularization? Higher light gives more ROS production. Why should greater amount of light give more ROS? Photo bleaching at high intensity. Then the classical cycle, the retinal cycle, this one, where it has to go to the retinal pigment epithelium, this takes hours, whereas your recovery time is too quick. Alright? So then transmembrane potential variation. Why should rhodopsin get phosphorylated? Many times it is observed, and oligomerized. Why should many rhodopsin come together? So how can we explain why should transducing change, alpha transducing change its affinity from JDP to GTP upon light infinity? Now, so here The murburn model is like this. Light hits the retinal pigment in rhodopsin, makes superoxide. It can easily make that. So GDP gets phosphorylated, transducing, that is inactive alpha. GDP becomes GTP, and then GTP becomes unbound. This serves as the messenger, not the alpha transducing itself, detaching and going as a messenger. Protein-protein complexation and all is too much. It doesn't make any sense in time frame. The protein molecules cannot go like that, and it's too deterministic. So this small GTP can go and go to the immediate beta transducing, and it gets hydrolyzed. Then by GDP releases, then that goes and interacts with the phosphodiesterase, which is like a clipped molecule, which releases. This is it. So another version, you see, effective charge separation occurs. This is the basic murburn theory. So from light, you have a direct oxygen-aided electrical transduction. That is something there was no charge, now you get a charge. So this is mobile, and that will reflect in a charge. So this can also phosphorylate. The GDP to GTP conversion is easy. Now you get GDP, and then it can give rise to the cascade. Now how do we show it? Very clearly, what are the evidence supporting it? This, if conformation change and all that is so important, you would not expect this to be very highly, but then the rhodopsin structure is not highly conserved. Alright, oligomerization is applied, as we have seen in respiratory system. Many respiratory complexes come together to minimize the radical production zone. So one radical can be immediately scavenged by the other redox active moiety. And you can see the structure where the reactive species can easily go, and that explains the proximity, the GDP, the docked GDP, so picomolar to GDP, the molecular affinity changes. So alpha transducing becomes after phosphorylation of the bound GTP, it loses the affinity. So GTP detaches. So GTP detaches. You see, now you can explain the structure of. Now you see here, alpha from here through the hole it detaches. Immediately beta. Here currently there is no role whatsoever given to this. They don't know what beta GTP does. So the murburn model clearly gives a very clear solution to that. That ROS comes here, the GTP detaches and their GTP is hydrolyzed. This has got very low affinity for GDP, but higher affinity for GTP. So docking very clearly gives the structural, the binding affinities, the signaling cascades, and now here also phosphodiesterase, same, all predictions of murburn. I told Danny, check this, and everything came as per the prediction. Alright? I predicted this would be like this could be like that, looking at the structure, just by imagining that oxygen is directly involved. So there you go. That's a very simple cascade for visual cycle. You don't need protein complexation, recycling through the retinal pigment epithelium. This is very fast. Alright? So ROS can immediately cycle the electron deficiency and all that. So this is the same thing, same retinol, the carotenoids are present in photosynthetic pigments also. In that also, the same mechanism. Alright? You don't need to invoke upon conformation change. So I think we are already close to lunchtime. So what I do is I'll go quickly over electrophysiology. I'm sorry. Neurophysiology and electrophysiology we'll go quickly over. Now, classical theory is in homeostasis. The membrane protein somehow can quantify, recognize, and translocate. Then there are pumps, porters, and pores. And then somehow, with all these things together, a cell membrane works like a very intelligent system. Alright? So the classical perceptions in electrophysiology is like this. There is a difference. There's a high amount of sodium outside, lower inside. So that gives an ion differential. And so in the there is Jens who found this sodium potassium pump, which pumps sodium outside and potassium inside. That results in this kind of a status. And then calcium also forms. So this pumping is the salient hallmark of cells. It uses a huge amount of ATP. Alright? So this is the classical setup. And now when you have something like this, there are link channels that push back the potassium out, and then that results in a negative potential of minus 70 millivolt, which is the resting membrane potential. Now, when there is activity, when the signal goes through the Hodgkin membrane, neuronal model says there is sodium gates opening, coming in, then gates closing, and then potassium going out, and this goes on in a very orchestrated manner along the neuronal membrane, and this gives the action potential. This is the classical way in which your nerves are supposed to work. So this is the one that started everything. In 1950s, Hodgkin and Huxley they did this work, and in 1960 or something they got a Nobel. After that, 9 Nobels were given to justify further enforcing these kind of ideas. This is the Cambridge School of Thought. So basically, transmembrane potential can arise in a wide variety of ways, and the difference in the ions, basically the ion movements, the cations are the rationales for the membrane potential difference in the classical theory. We cannot blame it also. They found that certain ions were more mobile, supposed to see more, going across membranes. But then, if you see basically the concentration difference and all that, somehow it doesn't make sense. And then there is, what would happen if you understand ionic pump without the channels? It says it pumps out, and then there are channels that bring it back. So somehow it doesn't look very appealing to me. Basically, this is the one that looks like a pump, kind of a pump. It's like you pump it. So first it binds sodium, 3 sodium inside, and then it uses ATP, pumping the sodium out, and then somehow it changes the affinity for that same binding sites. You get the same potassium coming back inside, and then things like that. So Freeman Cope and Tussle was apparently settled by Jensko's discovery. This guy, I think he committed suicide because of the issues of Freeman Cope. So if mechanism of the sodium potassium pump, NK is called Na potassium, that is K ATPase. That's what is abbreviated here. Is it a molecular motor? If it is a molecular motor, you would first need it to bind ATP. There should be gating. Some gate should open, it should take 3 Na in, then that gate should close, then it should go inward, then some gate should open, it should throw it out. All this, it should prevent. It should be a very, very, very sequential, one after the other, very clearly designed kind of hyper-intelligent kind of a protein. So but the point is, when you see the structure, you don't see anything that resembles that requirement. This is what it is. This is the NK. It's a very porous. I have multiple pictures to show. But then let's just imagine, what if, just think about it from a layman's point of view. It says 3 sodium is pumped out, 2 potassium comes in. And if it has to maintain a steady state, that means the active role should be countered by a passive mechanism. Only then you will maintain that. So, it's just a mirage board going around. There is no evidence. It says passively it will be coming back. And is there any evidence? Is there any evidence to show that 3 sodium is pumped out, 2 potassium is pumped in? Nothing. It's just a consensus. And also, it doesn't make any sense in terms of a mirage. You remember the picture that I showed you yesterday? The water flow. It just means this. 1 potassium is less. 3 sodium goes out, 1 comes less. So there is some kind of positive outside, an image is created. The active role must be countered by the passive role. How does it happen? Why should it happen? It just happens. So it's a wasteful process that just, have you heard the Sendil Countermany jokes, they have banana in one hand, he goes and takes, gives a banana, how much for this? 30 rupees. He says, you give that. And then, how much for that orange? 30 rupees. And you take that orange, 2 oranges. Then say, how much for that apple? You take that apple and then give back the orange. Where is the money for the apple? Somebody asked. Say, I give 2 oranges in lieu. And then when you ask for the orange, you say, I didn't take the orange. Some kind of a vague accounting. This is precisely that. So, the problem nobody looked at is the thermodynamics of the ions involved. Very clearly, there is very clear difference. Potassium is a larger ion, so sodium ion is a smaller ion. These are the different features and the solubilities in terms of the molar. You see, while chloride ion has comparable values, phosphate ion, acetate, carbonate, bicarbonate, carboxylates of proteins, all of them preferably solvate better with potassium. And potassium has the delta G of formation of this potassium ion is this. Much different from sodium. So these aspects and its interaction with the reducing environment and the interaction with oxygen is what leads to potassium's favorable presence in the cell. It's not other. And then the transmembrane potential is by virtue of the small amount of ROS. So we have gotten a simple equation based on that. And this was the scenario before murburn concept came into it. There were 3 theories. There was the membrane pump theory, the association induction hypothesis, which was formulated by Gilbert Lynn, to which Laurent Jakin, Hiroisa Tamagawa, whose message will be played here. He is also a very passionate person. He has got an equation that explains this part. That is how transmembrane potential is made. There is a GHK equation, Goldman-Hodgkin Katz equation, which defines the resting membrane potential. So Tamagawa had made a Tamagawa equation based on this theory. So along comes, see here ions are pumped, here ions get absorbed. In this there is effective charge separation, and this also accepts absorption. It doesn't say that absorption is not an important thing. So what we showed, Hirohisa Tamagawa in Gifu University showed, based on a simple suggestion, he showed just production of ROS can give transmembrane potential fluctuation. So the reality is that across spectra, the ionic differentials don't really correlate with transmembrane potential. What the classical theory does is it creates a membrane potential constants and somehow fits experimental data. So I'm not going into the details of this. This is the structure of the pump. You see how porous it is. How porous it is. How can there be any gating in this? It's just people seeing things, emperor's clothes, it's a very fine fabric. You will see only if you're a connoisseur. That kind of thing. I'm a young kid who says Raja Nangai. So here are the cardiotonic, toxins and all that that's supposed to bind. Here are the channels, potassium channels. The channels are not made through the protein. They are made between the proteins. So here is where Bob McKinnon got the Nobel, where potassium is somehow stabilized in certain ways, in certain dimensions. The only problem is if this is selective for potassium, the way McKinnon says, I made calculations. It will take at least hours to years for one potassium to go through if it has to be selective in the way it is. Binding requires time and selection, all that requires time. It has thermodynamic cost also, dehydration of ions, then rehydration of ions. It's not that easy as people are given the. So what the murburn view says is this one. The phospholipid, there is electrostatics, the phosphate ions of the lipids, they keep the anionic part inside, and so you have greater propensity for the potassium to be inside more. Alright, so here is the structure. There was once again, there was this is the main alpha protein subunit. There's a beta subunit. There was no role attributed to it. We saw that it has a high amount of lysine and arginine. So it's a ROS recruiting system which can sieve, thermodynamically sieve sodium and potassium. That's what it does. See, this is a very simple mechanism how some proteins, amino acid side chains, positively charged amino acid chains, a preponderance at a very simple location can achieve such kind of sieving. So there is a large amount of data which shows that phosphorylation on NKA is also seen at the intermembrane, transmembrane region. That is how we have ROS here. That ROS recruitment simultaneously leads to this also. So, like what Danny showed in NDH, this NKA modulator, such diverse range of NKA modulators. See the molecules that are supposed to modulate. They are all redox active, that's the only thing. It's not a binding based one. So, simple NKA structure, oxygen sensitivity, it's an oxygen sensitive enzyme, uncouplers, those uncouplers that were supposed to work in all the other systems also work here, and NK can also do ATP synthesis and transdermal peptide. This peptide has lysine, histine. This is also active. It also messes with the activity. So application of murburn in some people with neural disorder, you can lithium is here, but the reverse potential you see it's closer to the what is it? This is sodium. This is oxygen. These are the values. Lithium, the value of the thermodynamic delta G value explains closer to the value of potassium. So you have better explanation of that. See here, this is the cardiotonic steroids that digoxin, ubiane, bufalin, those toxins. Now they are supposed to go and bind at this place and somehow block those specific gates and all that. No, this is, in that case you should have steroids also messing with it, because it's the basic fabric is that of a steroid. So we, there are molecules that don't have the steroid backbone, but they have the what is that called? Quinone, flavone. What is that? What is this molecular structure? Cardenolide and bifidinolide. This structure, this is reactive oxygen species or DRS, interfacial active. So any molecule that has that, it serves. So many molecules that have. So it can both position better there and also do interfacial activation. So in murburn model, NKA is a interfacial ROS dynamic modulator. I quickly go over neurophysiology, I'm sorry. I've already done this. This is what it is. So but the problem is, what is the critical question that you need to ask? See, simple, this is called Fox microspheres. Those that don't have pores, all those, they also show exactly the same kind of action potential without pumps and channels. Why do ROS affect these outcomes? These are the questions that need to be asked. So we recently modeled based on murburn. We modeled reaction, relaxation, transport based, electronic, not ion pump based, not ion movement based mechanism. This is the equation. I will not go into the details. So basically, what happens there here is, in the classical primary carrier is ions, in its electrons and errors. Voltage is the driver here, it is a derived one here. Energy source is ion gradients. See, it's cyclic. Ion gradients give voltage, voltage gives ion gradient. There is no causation, no cause and consequence correlation. Continuous redox metabolism. The oxygen's role is direct here. Then the ion flux is a primary, it's a secondary buffering activity. Prediction, it requires channel gating, just redox sensitive excitability. So take home message is, sorry, there was another picture, I don't know, I made this yesterday night. So something has gone, there was a picture to show you the basic outlay. But on the classical model, ion channel centered explanation, in the murburn model, it is neuronal electricality emerges from redox mediated electron dynamics, links metabolism, oxygen, reactive species, and excitability within one framework, makes experimentally testable predictions on oxygen, Ross, ion strength, D2O, and temperature. Lots of data we have. This equation is beautiful in the sense that with 4 or 5 variables and parameters, we can catch the whole transmission velocity effect of all these parameters, whereas Hodgkin-Huxley requires 40 odd terms to get there, and there it is ionic currents. Just imagine this. Now you have suppose you imagine this is the axon. Hodgkin-Huxley is about this movement of ion from here to there. Murburn is from here to there. Where does the message go? Goes from here to there. Very simple. So while it measures ionic current based on transmembrane voltage fluctuations, this is a oxygen-centric, electron-centric process. I'm sure you will have a lot of questions. I open up. That's it. This was put together because there was somebody else, somebody else. I had to somehow fuse 3 agendas, that is vision, electrophysiology, neurophysiology, all just in one night's preparation. So that's why I just put certain things that are clearly discernible. I did not go too much against the neuronal model because it's very touchy to some people. But then let's see the point that to have ions go in and out, first you pump ions, generate a voltage. Then that voltage controls voltage gated channels. I mean, on the same membrane. How does it make sense? It doesn't make sense, to me at least. So that's why I questioned it. So there is an active process which generates something, and the passive process exactly counters that in various conformations, in various geometries. How? Why? Just because some people say. So here you have any signal, whether touch, vision, everything changes oxygen superoxide equilibrium. That's the most fundamental way. Or the only thing you have, every cell, what comes in? Oxygen and nutrient. And what goes out? Carbon dioxide and water. This is the machining logic of every cell. Whether it is a neuron, any cell, that's how it works. So it has to maintain. So changing the potential, the electrical activity is an outcome, it is not the driving force. Suppose if a scooter runs, imagine a scooter runs, it makes sound, it gives out smoke. You don't say when it makes a huge noise, you don't say, oh, the scooter runs because it makes a huge noise. It's just an outcome. Similarly, the voltage that you get is a dissipative outcome. It's just an associated phenomenon. What really is driving the process is the redox process that occurs within the cell. The complications are too much and too little time for me to present at this juncture. I finished my talk. We are all waiting for lunch. I know 1:45 already, late already. I can take a few questions. Sir, it somehow appears to be much better than the classical one.
Anybody online if you want? Anybody is there?
Yes, there is online. Can you show who's online? Mahendra Kavdiya teaches this in Wayne State University. Is Mahendra online? We have done this work together. So Mahendra, would you like to say something, please?
I would just say that Murali, you have some quite gifts, and I think you are doing really good, and you'll change certain things. Only thing, because I teach and did things in electrophysiology, and I have really understand the sodium potassium channels and electrical currents and all those things. So what I can tell you is my collaboration with you is mainly to make sure your numbers are correct and your basic things are correct, and to now I haven't found any faults or something, so which is good.
That's good. Thank you. Yeah. Tofia did her master's in VIT where I used to teach. Now she went to Rostock where she has been doing this electrophysiology, neurophysiology work. She works with computational simulations. Recently the equations that we derived, she did some simulations with that. We sent this paper to PNAS now. Our papers, both papers came back after about 4 weeks. Standard rejection. No comments, nothing whatsoever. Today I got my second paper of the flagellar model also. I sent 4 papers, 2 on bacterial flagellar model, quantitatively sound, beautifully derived. Both were rejected without any rationale. So Tofia worked on that. Maybe Tofia, you want to share some comments?
First of all, I would like to thank Melissa for giving this opportunity to be a part of this interdisciplinary work. And it was something which interesting to work on, because I have been brought up with the old classic neurophysiology concept. And when he introduced me to this new, it took me some time to actually go through it and try to accept what he wants to say, but eventually he was succeeded in actually convincing me, and I'm really glad that I am a part of this whole framework. And one thing which I wanted to actually tell, I think is a right platform, because it can be used a lot in some sort of neurodegenerative diseases like ALS, and I am trying to simulate that as well. And to some extent, I have got some positive results, and I'm just trying to. I can share this with Melissa later if he is interested. But I think it has a lot more. The scope is really vast, I would say. Because we are moving into really a paradigm shift in this area, and I know it's not easy for most of the people to accept at the first go. But I think it has a convincing approach, and eventually I think people will definitely accept it. So I'm really thankful to Melissa to give me a chance to be a part of it. Thank you so much, sir.
It's wonderful to see you, Tofia. It's how many years? 2008 to 2010, right, Tofia?
Yes, 2008 to 10.
Yeah, almost 16, 17 years. Yeah, I'm so happy. It's a teacher's joy when your students who are, they come around and accept your ideas, and that's how I said that, earlier, tigers, I said this yesterday, tigers are much stronger. How do we pass on the baton? Our kids, they take up, they spread the news, and wonderful. I'm happy that you took it up and you have done that ALS work, and hopefully this mathematical thing that we have together, and also the fundamental ideas, textbook ideas, will give us greater insight into the neurodegenerative and all those disorders. So thank you. Mahendra, you want to say something else?
have been working in nitric oxide, oxygen transport, and reactive oxygen physics for the last 25, 30 years, and it has always been a question why reactive oxygen species has to be there and what is the role of these. And more and more recently, people are started thinking reactive oxygen species as a signaling molecules, and your murburn concept comes completely in terms of that perspective that reactive oxygen species are very useful for human physiology.
Thank you. I completely forgot. Sukumar sir is my co-author in this neuron paper. I am so motivated. Sir, Sukumar sir, can you hear me? Sir, can you come on?
Yeah, I can hear you.
Yeah, he is the guy who fixed my errors in this first. Sir, please can you come online? You, can I see you? Yes, he is a quantum physics chemist. So earlier he was also looking at me with a lot of askance. Somehow I convinced him to join.
Well, I still look askance.
That's what scientists do. Yeah.
I wouldn't call myself a convert yet.
Yes, yes.
Although I did enjoy many of the talks today, and things started making a lot more sense to me. But as you said, I'm a quantum chemist. I'm not a biologist, not even a biochemist. So many of the terms, many of the ways of thinking are due to me. My role has been essentially to play the devil's advocate, to try to poke holes and things like that. And I think it was it might have helped in some way because as
it has. You bet it has. And
but still there are things that need to be patched, like where the equation comes from. I mean, you started out with a derivation, but that's not really the thing. And when Abhijit introduced the non-linear terms,
that is the last part.
But we have to show where that comes from, from a fundamental level, right? Right now it's a phenomenological equation.
Yes. But it's anyway better than what we have. Yeah, give it, sir.
Yeah, I'm not the person to speak.
Okay, fine.
Starts to trivialize the message when you're dealing with a professional audience. With students, to inspire them, these little analogies, help. But if you try to put that in a paper like you did, But anyway,
wonderful. So Professor Yanyu Wu is actually a photosynthesis person. It's the next session. Professor Wu, are you there? No, I think he might. Oh, yes, I'm here. Oh, wonderful. Can you show us your? I want to see you if you can come. We have worked on photosynthesis.
Sound is not clear for me. So can you increase the quality of sound, please?
Volume.
We can hear you all right.
I thought you can hear me in China without the mic. I speak so loud. Usually. He's from Chinese Academy of Sciences. Please.
Yes. Hello?
Yes, we can hear you. We can hear you. Hello?
Now muted. Maybe signal.
I think he's muted.
Professor Wu, you are muted. Can you unmute your mic, please? Anything else you want to say, Tafia?
Hello?
Yes, sorry, Tafia.
Yes.
Please come out. Yes, please.
Sorry, this is first time to use Zoom here. We usually use Tencent, so hello?
Yes, we can hear you.
I have a problem with connections.
Professor Wu,
can you please give me some opportunity to receive my connection as I have a problem in connection now?
Okay. maybe we can reconnect after some time in the photosynthesis section. Is that okay? After some time? He's a plant physiologist, and that's the next session. He has joined earlier. He's from Chinese Academy of Sciences, and we are one of the few who had some contesting issues with the classical model of Z-skin and some bicarbonate fixing mechanism, bicarbonate utilizing plants. I think Professor Wu can connect later. He has some issues. So, Prof, if you want to say something, you can say, and we will come back to the place.
I would like to ask Melissa whether it's okay if I present this concept here in the university, in the neuroscience department.
Absolutely, my child. Go ahead.
Yeah, thank you so much. Because I want to, with the ALS, I want to give them, because it has a big neurodegenerative faculty here. So I want, and it's an upcoming seminar. So I thought that why not to introduce this concept here.
Go.
Thank you so much, sir.
I called her my child, but she's not so young.
So, any question? Student?
Good. Yes.
Any question?
Danny, you're raising your hand? Oh. Lunch. So, sir, please.
So, it was all a wonderful presentation, and we had a great discussion. I think the numbers are as well. Produced in huge quantity. Retina is part of the central nervous system, so it all explains very well. And secondly, you have to understand that when you think to move your feet, this happens in less than a second, right? The moment you think, you can move your feet. Now you think about that, if it is the ions which are moving across, if the ions are the one which is moving across, it will take more than seconds to reach the signal to move your muscle to make a movement, right? So then how this thing is happening? Think about it. If it is ions in a potassium ion, sodium ions, etc. is moving across, the sodium and the potassium channels, you have the nodes of Ranvier which are, I call it as amplifiers of the signal, and if they are sitting in those areas, if it is movement of the ions across, it is practically very difficult for you when you think. Momentously, you can move your hand. The best example is that all of you have watched cricket. The guy who is standing right in front of the batsman, how he does the reflex action catching a ball which is coming at more than 100 miles per kilometer per hour, hit, and then momentously catching the whole thing. If the ions have to move and then do the whole job, it is practically difficult. So you have to have an explanation for this, because the thing is happening. So what is the other explanation? Here comes the electronic movement. And this is what needs to be explained in detail with a much more experimental evidence. And in neurodegenerative disease, because that's one area which we work heavily, we can see all these channels. It's beautiful clusters. Sodium channels are clustered beautifully at the node. You can see in the juxtaparent node the potassium channels in between the Casper protein, etc. They're all organized beautifully. But the moment demyelination happens or the neurodegeneration happens, all these things are declustered completely. And you can see no impulse conduction, etc. So what these channels are doing actually, they are providing us a platform for the reactive oxygen species to play their job. This is what we think, And God, you may agree with that. Thank you.
Yes, I think, sir, will you have the chair?
So, I think if nobody has any questions, anybody has any questions? If nobody has any questions, we will wind up. And thanks once again for inviting me. Thank you very much.
Thank you, sir, for coming.